begin recording, and of course I'd like also to share my screen. Okay, perfect. So I hope that you see my screen now. It's okay. Okay,
Yes, it's okay.
perfect. So I would like to complete the analysis of the force method by showing you the main application in the practice of the force method. So the application to continuous beam. The application to continuous beam is probably the most important application because first of all, we can obtain a generalized approach because you see our structure is made by a series of beams, and so it is possible to make this structure statically determined by introducing for each intermediate support like B and C by introduce an internal hinges, and correspondent to the internal hinges we can also highlight the redundant bending moment x1 and x2. Of course, if we have a lot of intermediate support, so we have further intermediate support like B, C, D, and so on, we can generalize this approach. So let's look at the internal support, and corresponding to each internal support we can introduce an hinge, and corresponding to this new hinge basically we can also highlight a redundant bending moment. Perfect. So once we have done so, as usual, we can apply, as usual in the application of the force method, but we have also seen this kind of application also in the case of the elastic curve. Basically, we apply the superposition principle. So we consider first the situation associated to the application of the redundant bending moment x1. Afterwards, we sum this effect to the effect associated to the action of the redundant bending action x2, and afterwards we can add also the effect of the applied loads. Okay, so now let's look to a more complicated beam. In this more complicated beam, we have basically 3 intermediate support. But of course, we can also consider a continuous beam with 27 intermediate support. Okay, so if we have 27 intermediate support, what we have to do is that for each of those intermediate support we can add basically an internal hinge, and we can basically highlight a redundant bending moment for each intermediate support. For example, you can consider that in real building, when we look at a frame which consists of several bases, but generally we have a number of intermediate support which might be larger than 3. Similarly, when we look to the world of bridges, at present most of bridges are continuous beam, and so we can have a lot of intermediate support. For example, when you consider a traditional overpass, which is a flyover across a motorway, for example. A traditional overpass consists of 3 spans. The central span is generally larger than the lateral spans, and the central span generally realizes the overpass of the motorway. intermediates. So the continuous beam with several intermediate support is a static scheme which is very often met in real application. So, for example, let us consider a continuous beam of 4 bays of 4 spans with the 3 intermediate support. Okay, so what we have to do is let's look to the 3 intermediate support, and for example, let us denote the 3 intermediate support with the number 1, 2, and 3, as you can see in this slide. And of course, in order to unequally denote also the beams, for example, the left-hand side beam is denoted as beam number A, the second one is beam number B, the third is beam number C, and the opposite right-hand side is beam number D. Afterwards, we have to make the application of the superposition principle. And first of all, we apply the external load. The external load in this case is, for example, an external loads and uniformly distributed loads that is bearing the 2 beams A and B. And so, for example, we have rotation corresponding to the intermediate support number 1. And so we have, for example, this rotation phi10A and phi10B, that are the 2 rotations at the opposite sides of cross-section number 1. The first is belonging to beam number A, and the second one is belonging to beam number 2. Of course, we have also to consider what happens in point number 2. And in point number 2, we have a rotation that is denoted as phi20B. Afterwards, we have to consider the effect of the first redundant action x1 made equal to unity. And so, still, as in the previous case, we have to consider the rotation phi11A as well as the rotation phi11B. And in addition, in point number 2, we will have the rotation phi21B. Okay. Now we have to consider the application of the second redundant bending moment x2 make equal to unity. Of course, this redundant bending moment generates a relative rotation corresponding to cross-section number 2. And so we will have a relative rotation phi22B and also a rotation phi22C. But of course, there are also rotation corresponding to cross-section number 1, and this rotation on our left-hand side is called phi12B, whereas the rotation on the opposite side will be equal to phi32C. Remember, always this rotation, this flexibility coefficient are denoted by 2 subscript. The first subscript is related to the points, and the second subscript is related to the position of the unit bending moment. In addition, we have also another superscript which is related to the beam A, B, C, and D corresponding to the beam to which the rotation belongs. Finally, in order to complete the application of the superposition principle, we have to refer to the action of the third redundant bending moment make equal to unity. And so we will have the relative rotation phi33C and phi33D, but also the rotation corresponding to the cross-section number 2 and belonging to beam number C. So the rotation denoted as phi23 beam C. Okay. Now we have to remember that corresponding to the three cross-section, in this case, called 1, 2, and 3, in the service structure, in the basic determinate structure, we have an hinge, but in the real structure there is continuity corresponding to this intermediate support. And if the cross section and the intermediate support are continuous, this means that there will be no relative rotation between the left hand side and the right hand side of cross section number 1, and similarly there will be no relative rotation between the left hand side and the right hand side of cross section number 2, and similarly there will be no relative rotation between the left hand side and the right hand side of cross section number 3. So if we are going to look at cross section number 2, let's sum up the relative rotation. So the relative rotation corresponding to the action of the external loads is phi10A plus phi10B. So this first term, we have to sum up the effect of x1. And so this effect will be equal to x1 times phi11A plus phi11B. And finally, we will have the effect of the x2 times phi12B. Of course, the summation of these three series of rotation will be equal to 0. Why? Because there is not an hinge corresponding to this cross section, but there is continuity between the left hand side and the right hand side, and so the rotation of a continuous beam above an intermediate support, this rotation will be continuous. This will be equal on the left hand side and the right hand side, so no relative rotation, and so this summation will be equal to 0. Two similar conditions needs to be written for the intermediate support we have denoted as number 2, and the intermediate support we have denoted as number 3. So let's look at the intermediate support number 2. Okay, so effects of the external loads, phi20B, and here we have phi20B. We have to sum to phi20B the effect of x1. So x1 times phi21B. So plus phi21B times x1. Afterwards, we have to make the summation also of the terms corresponding to the effect of x2. So x2 times phi22B plus phi22C. And finally, we have to sum up the last effect, which is the effect associated to x3. So x3 times phi23C, and also corresponding to this second intermediate support, the summation of all the rotation highlighted through the superposition principle, the summation of all this rotation needs to be equal to 0. Finally, we have to look at the last intermediate support, and we can observe that corresponding to the third intermediate support, there is no effect of the external load in this case, and similarly there is also no effect of the first redundant bending moment x1. On the other side, there is the effect of the second bending moment x2, and this effect it will be equal to phi32C times x2, okay, plus the effect of x3, and the effect of x3 is x3 times phi33c plus phi33b. Okay, so we have this series of three linear equations. So generally, when we apply the force method, and specifically when we apply the force method to a continuous beam, we will obtain a system of linear equations. The order of this system of linear equation, even in the general case, but also in the case of a continuous beam, the order of this system of linear equation is equal to the number of redundant reactions. Of course, since I have a system of linear equation, I can express this system of linear equation in matrix form. Generally, when we use the matrix form, in matrix form, a square matrix is denoted by a letter. Generally, it might be a capital letter with two underscore. Okay, generally, when we refer to a vector, the vector is denoted as well by a capital letter, but we can distinguish a matrix and a vector because the matrix is denoted by using two underscores. The vector is denoted by using just one underscore. But the interesting aspect is for a continuous beam, the shape of the matrix of coefficient, of flexibility coefficient. Because, for example, if we are dealing with a 3x3 linear system of equation, the matrix form has a terms which is different from 0, corresponding to the first unknown and to the second unknown. And let's look here. So different from 0 here, and the term different from 0 also here. Corresponding to the third unknown, we have 0. Okay, let's look at the second equation. Corresponding to the second equation, we have that this point multiplying by x1 is different from 0, but also the terms corresponding to x2 is different from 0, and also the terms corresponding to x3 is different from 0. So if we look at the second equation, we have a term that is different from 0, corresponding to the first column, second column, and third column. Now let's look at what happens in the third equation. And corresponding to the third equation, we have that the term corresponding to the first column is equal to 0, whereas we have terms that are different from 0 corresponding to the second column and to the third column. If we increase the number of equations, because the number of the redundant terms is increasing, what we can observe that the maximum number of terms that are different from 0 is equal always to 3. And so for each added equation, we will have a maximum number of terms that will be different from 0 that it's equal to 3. So when we have a matrix like this, we can call this kind of matrix a three-diagonal matrix. And generally, solving a system of linear equation with a three-diagonal matrix, it's quite easy because we can start from the last equation in which there are only two unknowns, basically, and so we can express one unknown in terms of the others. And then we can move with the back substitution from equation to equation. And so it is very easy to solve a linear system with a three-diagonal matrix of coefficient, like in the case of a continuous beam. If we have a different initial system, an initial system which is different from a continuous beam, of course, we will have a matrix of flexibility coefficient that will be not a full matrix. So it will be a matrix still containing a large number of zeros, as you can see in this general form. But the matrix will be no more a three-diagonal matrix. When we refer to matrix form of the force method, generally the matrix of the coefficient, of the flexibility coefficient, since it collects coefficients that are called flexibility coefficients, this matrix is called flexibility matrix. Okay? Afterwards, the vector x in our cases contains some redundant bending moment. In the general case, it is possible that that vector collects redundant forces. So in this case, the x vector is a vector that collects bending moment of forces, and so it is called vector of the generalized forces. So let's look at the vector on the right-hand side. The vector on the right-hand side, collecting some terms that are knowns, is collecting some terms that, in case the unknown x are bending moment, are rotation. In case the redundant action are force, might be displacement. So it's a vector generally collecting some generalized displacement. Okay? Of course, we have already discussed several times the mechanical or physical meaning of the equation, allowing us to write the equation in the force method. Those equations in general force represents compatibility conditions. Okay, so they represent the fulfillment of the constraints condition that are prescribed corresponding to the external or internal constraints condition. But it is interesting also to observe this compatibility equation, because here, corresponding to the vector x, we have some generalized forces. And corresponding to the known term, we have some generalized displacement. But of course, it is possible to make an inversion of this linear system by evaluating the inverse of matrix F. If we evaluate the inverse of matrix F, it is possible to express x, which means some generalized force, as a product of the matrix of the inverse matrix of F times the displacement. So in this case, on the left-hand side, we will have forces. And also on the right-hand side, we will have a product of some coefficient multiplying some displacement. So also the right-hand side will contain some generalized forces. So when we write the equation of the force method in a direct form, those are compatibility equations. But if we make the inversion of the flexibility matrix and write the equation in this form, x equal to the inverse of matrix F multiplied the displacement, the vector of the generalized displacement, this equation is an equilibrium equation. So it's a system of equilibrium equations. And generally, the matrix, the inverse of matrix F is denoted as matrix K. The matrix K is called stiffness matrix. And so this say also to us that it is possible to formulate something which is in a certain sense very similar to the force method, in which some equilibrium equations are forced. As you have heard from Dr. Ruccolo on the next lecture, the characteristic of a software code will be explained during the lecture. Of course, this kind of software will implement the solution of some equilibrium equation, okay? And generally, when we apply the methods for solving highly redundant structures, generally we do not apply force method, but apply a different kind of methods that are belonging to a different family, and this family is called the family of the displacement method. Before showing you some limitation in the application of the force method, I would like to remember you the last exercise Dr. Ruccolo has shown to you. Because in this case, we have a frame structure, and it is very interesting to observe that in order to obtain an application of a general application of the force method, it is necessary to apply an internal hinges corresponding to this point. But when we apply an internal hinges that is passing and interesting three beams, what we are doing indeed? We are basically applying an hinge between the horizontal left hand part and the horizontal right hand part. And so, for the effect of this internal hinge, we have to apply a first redundant bending moment, and we can denote this first redundant bending moment as x1, for example. But when we apply this internal hinge, we are also applying an internal hinge between, for example, the right hand side beam and the vertical columns. And so we have to apply a second redundant bending moment that is denoted as x2. And x2 is acting between beam number C, which is the vertical beam, and beam number B, which is the horizontal beam on the right hand side. Okay, so please remember this kind of highlighting the redundant action. The solution of this structure indeed is very simple. Why is very simple? Because beyond the value of x1 and x2 of the redundant action, what I can see very easily is that this structure is symmetric with respect to this vertical axis. And if this structure is symmetric, it means that this node does not rotate, okay? But if this node that does not rotate, it means that the vertical columns will be subjected only to a vertical axial force. And we already know the bending moment, the redundant bending moment corresponding to the left-hand side and right-hand side beam. Okay, so in order to demonstrate this, we can apply the superposition principle. And so when we apply the superposition principle, okay, we can say, for example, that first of all, there is the action of the external loads. In the action of the external loads in point number 1 will be the generation of two rotations, phi10A and phi10B, because I would like to denote the left-hand side beam as A, the right-hand side beam as B, and the vertical column, as I said, as C. Afterwards, the redundant bending moment x1 make equal to unity will act, and so we will have this kind of effect, phi11A and phi11B plus x2 times the effect of this bending moment made equal to unity. And so we will have a rotation phi12B in the right hand side beam and phi12C in the vertical columns. Afterwards, I will apply the compatibility condition. And the compatibility condition are, of course, related to the, first of all, there is no relative rotation between beam A and beam B. So the relative rotation between beam A and beam B are phi10A plus phi10B. And here we are, phi10A plus phi10B. Okay. Afterwards, we have the effect of the bending moment x1 made equal to unity. And here we have the two rotations, phi11A plus phi11B. So phi11A plus phi11B times x1. Afterward, there is also the effect of this bending moment made equal to unity. So plus phi12B times x2. Afterwards, I have to consider that there will be no relative rotation between beam number B and column number C corresponding to this point number 1. And so we will have to look at the different rotation. Of course, we have the effect of the external loads, but the effect of the external loads needs to be analyzed only on the right-hand side, so phi10B. Afterwards, we have the effect of this bending moment only on the right-hand side, so plus phi11B times x1, and afterwards we have to consider the relative rotation between the right hand side beam and the vertical column. So phi12B plus phi12C times x2. Okay. Afterwards, if we solve this system, we will obtain that x1 will be equal to minus qr squared over 8. And x2 will be equal to 0. But this solution was already known to us because it is the solution of a beam in which we have no rotation corresponding to the intermediate support. We have already examined the behavior of this kind of beam several times, and so we are capable of evaluating very quickly the distribution of axial force, shear force, and bending moment corresponding to this redundant structure once I have solved for the redundant reaction. Okay? But I would like also to make some comments about the limitation of the force method. In fact, I have already commented about the fact that by inverting flexibility matrix, I can obtain a different condition, which is an equilibrium condition. So it is possible to define a different method for solving the redundant structure. And in this method, displacements are unknowns, not forces are unknowns. And so this method is called displacement method. So let's look at the general system. Okay, this is a frame structure, and you can see that this frame structure is also exhibit some bracing. So for a structure like this, it is possible to obtain a statically determinate structure by introducing hinges corresponding to this node, these nodes, and so on, to all nodes between the different beams. By doing this, of course, I have made my structure is constituted by beams in which basically we have simply supported beams. So my structure consists of several simply supported beams. And this system is not redundant, it is statically determined. But let's look at another system without no bracing. If we try to do the same corresponding to this system, what we can observe that the system we have generated is not statically determined. And so if the system is not statically determined, I cannot apply the force method. And so I need to formulate different kind of methods in order to solve this kind of frames where it is possible to have displacement corresponding to nodes, for example, due to the action of horizontal forces. Okay, so today I have concluded very fastly my lecture, and so since what was scheduled for today has already finished, before leaving, I would like, of course, to ask if there are some questions from the audience. Okay, I'm sharing the screen. Let's stop sharing. I have